All right, well, we were in chapter 13 talking about vector fields, correct? And we had gotten as far as the idea of a conservative vector field, right? Am I giving you some homework there? So make sure my little audio is recording. Good, good. All right, so we're going to start 13.2, or no, did we? I just opened it and you looked at it, right? A little bit? No? We didn't. No, we didn't. Okay. So 13.2, line integrals. Integrals, it's misspelled. Line integrals, or what are called curve integrals. I really like this section, all right? We're going to be doing integration again. We've done integration before, but the geometric part of this I think is pretty cool. So let's take a look at what this concept is. Suppose that we have a function f of x, y defined on a curve C in R2. So just take a look at this picture for a second. We have, first of all, a surface, right? That's f of x, y. Then, if we do not restrict the domain, we don't restrict the domain at all, it's the entire surface in every direction, right? But if I just restrict that domain to some curve, meaning instead of plugging in all values down here on the ground, I just plug in some values along a curve, those values will get mapped up into the surface, and they will form a curve on the surface, right? All right. If I look at it from the top, those should be right on top of each other, right? Something like that. This is actually the surface 2 plus x squared y, and it's defined on the upper half of the unit circle. So you can kind of see that from the picture. I took the upper half of the unit circle and then plugged it in. So what we wish to do, what this is all about, is we want to imagine dropping what we call a curtain down from that curve down to the ground. If we drop a curtain down here, like that, then we have a new surface, right? A green surface is like a curtain, and we're going to want to know what the area of that is. So going back to Cal 2, what we had in Cal 2 was we could have looked at it when we were in Cal 2, we were on a flat sheet of paper, right? But we could have really imagined that we were in three-dimensional space, just we weren't using one of the coordinate axes, right? So we were only using two of them. And what we did was we found the area underneath this curve by doing a bunch of rectangles and adding up those areas, doing a summation. So in Cal 2, to find the area, we did the integral from a to b of f of x dx, where f of x was the height of the function and d of x was the width. So back here, the height of the function is f of x, the width was dx, the infinitesimal width of the rectangle. Yes? All right. The difference here is, well, what is the difference between this and this? It's not flat, right? It's not flat. So down here, that curve makes all the difference in the world, right? If that was a straight line instead of a curve, we would be like we are here. So this down here was a straight line. Our dx here was always the same, right? The same width, same width, same width the whole time. Dx was like constant throughout the entire thing. Of course, they got smaller and smaller and smaller, but once we set the rectangles, each width was the same. If we are going to go around a curve, then what do you think we're going to incorporate? dy, yes. We did this a while back, though, didn't we? If you go along a curve and I want to know how long it is, right? It's going to be like a little arc length, isn't it? So that's somehow going to come into play. So what we need to do first, and this is going to be I guess the challenge of the problems, is we need to use parametric equations to represent our curve in two-dimensional space. So we need to be able to draw our curve on the ground that half circle, we need to be able to draw it using parametric equations instead of like y is a function of x. So that it's more like we start the clock and it starts drawing the curve. So t will be our parameter instead of x depending solely on, y depending solely on x. So if we can represent that curve, if we can represent that curve C in the two-dimensional space with parametric equations where our x is some function of t and our y is some function of t, and we restrict our t between 2 points, then we'll be able to do this. Okay, so there's that picture I was saying. We want to know the area of that rectangle right there. The height of it is just the height of the surface. That's f of x, y. But the width of the rectangle is an arc length. So the area of the rectangle is the height, which I just said, right? F of x, y. And now I'm putting x of t, y of t in here because I'm going to reparameterize my curve where my x is now a function of t. So this is going to be, there are going to be t's in here instead, and there's going to be some t's in here. And then delta c, where delta c is the arc length. And you'll have to remember what the formula for arc length was. Let's see, I'm trying to remember. Did we talk about arc length in here? We did, it's way back when. But we did arc lengths for vector functions, which was different. This is the arc length formula from Cal 2. That's what this is. So if you have an integral, right, that adds up everything, right? Look at our domain here. Notice it's a single integral. It's not a double integral. It's a single integral because what I'm doing is I'm integrating over what? A curve, right? As opposed to integrating over a region. So I'm integrating over a curve. What am I integrating? Well, these rectangles. These are the heights, and each of the widths is ds. S is going to be like arc length. So I'm differentiating with respect to arc length. Coming over to the actual conversion, a to b is going to be my restriction on t, the time variable. My f is going to be evaluated at the two parametric equations. So my x of t, my y of t. Then my ds is this. This is the arc length formula from Cal 2 for a parametric curve. So it's just a Pythagorean identity. That's all it is. Right? A squared plus b squared is c squared. So if you're trying to get, if you're on a curve, I'm trying to approximate the distance between those 2 points. I draw a right triangle. This is approximately dx dt, meaning how much x changes with respect to t. This is dy dt, approximately how much y changes with respect to t. And so this side of the hypotenuse would be the square root of this squared plus this squared, right? Which is this right here. And of course, if you let these get smaller and smaller, infinitesimally small, then that error that we had there goes away and you get the actual arc length. So that's where that comes from. Not going to get into it deeper. In Cal 2, you may or may not have, but it's a pretty simple result of this picture. All right, so that's all we need. Now this is called the line integral with respect to arc length. So when we see this, line integral with respect to arc length. Some things I'll point out again, just to make sure we're all clear. This is a scalar function we're integrating, right? F of xy is a scalar function. It is not a vector function, right? Because in a little while, we will be integrating vector functions, so we need to know the difference. This is a scalar function with respect to arc length over a curve C. It's called the line integral. Now, the line integral is not necessarily a good name for it. Do I say that in here? Thought I said that in here, but okay. The line integral is not a good name for it because it makes you think that you're integrating over a line. That's why in the very beginning I put curve integrals, because that's a better name for it, all right? So let's do this example. See if I can do what I did last time. I thought this worked out pretty good. You tell me if you like this or not. Seem like enough room there? Yeah? Okay. So I need to first get my head around what the curve is. All right? It's the upper half of the unit circle. I need to be able to draw that with parametric equations. So I'm going to start with that. And I'll work with the integral in a second. That's C. Now it's the unit circle, so this is 1 and this is -1. How can I draw a unit circle using parametric curves? So I need to come up with some function. X is some function of t, and y is some function of t. That as I let t change, it will draw me that circle. So cosine and sine, right? How about cosine t, sine t? Cosine t, sine t will draw that circle. And what about a restriction on t? I do want it to stop somewhere, don't I? I want t to start where? 0 and stop at pi, right? I don't want to draw the whole circle, so I want to restrict it. All right, so that's pretty clean parametric representation of that curve, right? Once you have that, it's pretty much just grind it all out now, right? The formula. So I'm going to need the derivatives of these, right? I'm going to need them to square the derivatives and take the square root and all that stuff, put it into the integral. So here's what I'll write so far. This line integral over C of 2 plus x squared y squared ds should be equal to the integral from 0 to pi of 2 plus, now what's x squared for me? Well, I have to replace x with what? Cosine t. So this is going to be cosine squared t, then times y, but y for me is sine t. All right, do you see that that is the original function, f of x, y, substituting our parametric representations of x and y in? And then I need ds. Now ds is probably going to require a little bit of work, so maybe I'll do ds somewhere else and bring it back here. Is that all right with you? I'll do in this top corner. ds is the square root. Is it all right if I say x prime squared plus y prime squared dt? Is it all right if I say that instead? That way I don't have to write dx dt, dy dt. What is the derivative of x with respect to t? Negative sine t, right? Negative sine t. But then what are you going to do? Square it. So this is going to be square root of sine squared t. Hey. And then derivative of sine t is cosine t, but then square it, so cosine squared t. Isn't that nice? Just one, right? Pythagorean identity. Square root of 1 dt, which is just dt. So my ds is just dt. It just so happens in this particular problem, that's what it is. Lucky for us. And this is just a calculus 2 pretty basic integral, right? You have to integrate with respect to t on this. So what is the antiderivative of 2 with respect to t? 2t. The antiderivative of cosine squared t sine t. Negative 1/3 cosine cubed t? Is that right? What's the derivative of this? Take the derivative. You get the 3 comes out, right? Gone. You'll have cosine squared t. Then derivative cosine is negative sine, so there's that. And then the negative comes out and hits that negative, becomes plus, so that should work. Now, how would you do that? just a u substitution. U is cosine t, and then rewrite the integral. But I would expect you could do that on your own. Okay. And then 0 to pi. So let's plug in pi. If you plug in pi, we get 2 pi. What's cosine of pi? -1. -1. Cubed is still -1, so that'll become a plus 1/3. Then you subtract from that what you get when you plug in 0. Plug in 0, you get 0. Plug in this 0 here. What's cosine 0? This is 1, so that's just -1/3 there. Did you have to wait for them to plow the snow off the road? Okay. We were all talking about that earlier. I believe that's what we're getting here. 2 pi plus 2/3. That would represent the area underneath that curve. Any questions? So, I mean, really, it's almost like a formula. The challenge will be coming up with the parametric representation of the curve, right? That'll be part of the challenge. Taking the derivatives and then the square root, hoping that that's going to be nice. In this case, it was just 1. We got lucky. It's not always going to be that. And then after that, it's just a regular old integral. There's no like double integral here. It's nice. All right, so the next note says, if C is the union of a finite number of smooth curves, remember smooth curves meant that, what did smooth mean? A curve being smooth, that was a little different. It had something to do with vectors. You couldn't have these corner cusp things even on a smooth curve. So if you have a finite number of smooth curves, C1 through Cn, then the integral over all of them is equal to the line integral of each one added up. Does that make sense? This is the geometric picture of it. If I want to integrate, my surface here is a plane, and my curve on the ground is actually like a parabola and then a straight line. Then the line integral over this whole thing is the total area of that curtain underneath, right? So it should make sense that you just need the area of the curtain above the curved part, right? And then add to that the area of this one. So this is C1, C2. You find the union, you find the areas of each one, add. Does that make sense? Geometrically, it would make sense that that's okay. That's all that theorem is saying. Now that's important because if I asked you to integrate, or if someone asked you to integrate this function over those two pieces, the parametric representations for these two things are different, right? They're different. You couldn't use the same parametric representation for each of those curves. So you would need to split it. That theorem allows us to do it. So let's do this example. Find the line integral over the curve C of 2x with respect to arc length, where C1 is the parabola y equals x squared from 0, 0 to 1, 1, and C2 is the line segment from 1, 1 to 1, 2. Here we go. Man. Now, I gave you the picture, but let's act like we didn't have that picture. We have the parabola y equals x squared going from 0, 0 to 1, 1. So that's C1 right there. And C2 is the line segment that goes from 1, 1 to 1, 2. So what I know from the previous note is that this integral should be equal to the line integral over C1 of 2x ds plus the line integral C2 of 2x ds. So I have two problems to do here. So let's work on the parametric representations of our curves. And we'll have to do C1 and C2 separately. So I'll split my page into two pieces here. Here's the line integral I'm going to do here over C1 of 2x ds, and then my line integral over C2 of 2x ds. So if we're going to do this one over C1, let's come up with the parametric representation of C1. Help me out. X of t, y of t. How can you draw the parabola? And then what are your restrictions on t? Remember, what was the parabola? It was y equals x squared. Anytime you have one of the variables solved for, this is the easiest parametric representation to do. Because all I have to do is replace the independent variable with t. So remember the idea of independent and dependent? Here, y depends on x. You give me x, you can determine y, right? So x is the independent variable, y is dependent on x. If you ever have that situation where one variable depends on the other, replace the independent variable with t. So I'm going to replace x with t. Okay, the x is going to become the t. So if x is t, what's y? T squared, isn't it? If x is t, then y is t squared. Then what's my restriction on t? Well, my restriction on t means what's my restriction on x? Because t is like x, isn't it? So look up here to my parabola. My x is going to go between where and where? 0 and 1, right? 0 and 1. And just to make sure you got that, what if this had said x equals y squared? Then you would have put what? This would have been t squared, and this would have been x. So it would have been the other way around. Sorry. This would have been t squared. This would have been t. If you have an equation that represents your curve, and one variable is written explicitly in terms of the other, then the independent variable, the one that is on this side with the complicated stuff, that's the independent variable, is just replace that with t. And then the other one becomes this equation, just t's everywhere instead of x's. Are we going to be able to take these derivatives, square them? Yeah, we're going to be happy about that. Okay, I'll come back to that. Let's get the parametric equation representation of C2. Maybe this one is so easy it's hard. A vertical line does not have an equation y equals anything. Like, right? It's not y is a function of x. Yes? I mean, so we could look at it as a function? In some sense, we are going to do that. Tell me what doesn't change here. If you're on this line segment, what doesn't change? Your x is always what? So can I just define the x coordinate to be 1? Now, what about the y coordinate? It's changing, right? It's going between 1 and 2, right? It's varying. So the y coordinate, I could call that t, and let that t vary between 1 and 2. And that should draw me that line, shouldn't it? Fix your x at 1. let your y be t, but let your t go between 1 and 2, and that'll draw everything. Notice that this parametric representation completely different than that parametric representation because they're different curves, and our time restrictions are completely different also. They don't have to be the same, which is why it's so important that we break it up into two integrals, because everything's going to be different, right? The derivatives are different here, derivatives are different there. Our replacement up here of x is going to be different than our replacement here of x. Any questions? All right. So let's get the derivatives and square them and do all that stuff. Let me go for ds now, because I know I'm going to need it. It's the square root of, all right, what's the derivative of x? So I'm looking here. What's the derivative of x with respect to t? 1 squared plus, now the derivative of y with respect to t, 2t squared, 4t squared, dt. So that's just square root 1 plus 4t squared dt. That's ds. You want to go get the derivatives for the other one now, or you want to just finish this one off? The other one? Okay. So ds over here is square root of, what's the derivative of x with respect to t? 0 plus derivative of y with respect to t, 1 squared dt. So that's just dt. And now let's go ahead and set these integrals up. Your first line integral is going to be the integral from where to where? 0 to 1 of 2 times x, 2t, right, because x was t, ds, which is square root of 1 plus 4t squared dt. So that is this one right here. And then plus, what? 1 to 2. 2x is going to be for us what? 2, right? 2 times 1? Because our x is 1 here. So this is just 2. It's a constant. And then ds, which was just dt. You could go the rest of the way. ... And then add the answers together. How would you do this integration right here? Basic u substitution again. I'd let u be the 1 plus 4t squared. The derivative of that is, 8t. You're off a little bit. You adjust things, scale. You're ready to go. All right? Then this one is comical, right? And we're done. Add the answers, you're done. All right, now there are two other line integrals that come into play, and we'll see later when. But we could do a line integral over C, but instead of doing it with respect to arc length, we could do it with respect to x. Now, geometrically, this is not necessarily going to be the same picture of the curtain that we had before, but we could still define this way. Everything is exactly the same, except that instead of having to compute that ds, which was that square root of all that stuff, we just use dx here. And that dx is just the derivative of the parametric equation that we have for x. So it's assuming, it's basically this formula that we had here. ds was this, dx dt squared plus dy dt squared. That was dx. ds. dx is just this whole thing again, but holding dy dt to be 0. So if you do that, that's just dx dt. Do y'all see that? So it's like you're not saying how much does this, the arc length is this length. We're really just looking at it with respect to this length instead, and saying that that's 0 this way. So that's the line integral along C with respect to x. Then with respect to y, now you hold your dx dt to be 0, and that means you've got the y prime out here. So you're looking at that piece of the triangle instead and making this one 0. Make sense? Yeah? Okay. The two previous line integrals often appear together in problems in later sections. In that event, we will use the following notation. So I have the line integral over some curve C. Instead of f of xy, I'm putting p of xy dx plus line integral over same curve C, different function q of xy with respect to y. We can write this way without, it's just a notation thing. When you want to do this, just write it like that. We understand that what you mean is you're going to do a line integral over C on this one and a line integral over C on that one, even though they're with respect to two different things, right? This one's with respect to x, that one's with respect to y. There's no loss of concept there of what we're doing. So just notation. That's all that is. So here's an example right here of that notation being used. I want the line integral over C of sine x dx plus cosine y dy, where C is blah, 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 blah. All right? So this notation means I actually have two separate line integrals, right? I have one with respect to x, one with respect to y. They're both going over C. So let's see what happens here. Oh. Probably should have been doing this all semester. I will write down what I need, though. I need line integral C sine x dx plus line integral over C cosine y dy. So I'm going to do those two things. However, what's C? Let's take a look at C. C is the top half of the circle x squared plus y squared equals 1, which is, we already did that today, didn't we? That's this again. We know how to find the parametric equation of that, don't we? Be nice if it actually looked like a circle. Yeah. Is that C? That's part of C, because it says it's this half circle, right, from here to here, then, and the line segment from -1, 0 to -2, 3. So here's -1, 0 to -2, 3. Bless you. Oh my goodness. It's so cold, I can't write. All right, there we go. So do I have the union, is C the union of two smooth curves? Yeah, and you see that this, you might say that's a cusp or something, but separated, when you separate the circle from that line, it's actually two separate smooth curves. So it's fine to do it that way. We'll call this C1, call this one C2. I'm going to do this problem a little different than the last one. I'm going to get my parametric equations now. Just get them all going on the side here. Tell me about C1. X is what? Cosine t. Y is sine t. And t is between 0 pi, right? We did that earlier, didn't we? So that's nothing new. That was the first thing we did. How about C2? Hmm. 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 Yeah. Uh, make a line, yes? Hmm. We could find the equation of the line, like y equals whatever. We could do that. I've got another idea for you. I've got another idea. See if I can find it. Ah, what are the odds that I open right to this? What are the odds that I open right to this section? What the heck is this? Check it out, man. I couldn't have got so lucky. Well, I guess I could have. Here's what we had. If we wanted to come up with the vector equation of a line segment between 2 points in two-dimensional space or three-dimensional space, we could define a vector function, right? R of t plus tv. V was the direction vector. R naught was one of the points rewritten as a vector. And we come up with our vector equation of the line, right? But didn't we say that each of the components of the line represented our parametric equations? That when you have the vector equation of the line, you could write it in what were called its parametric equations and then its symmetric equations. Now, this is way back. This is day 4, okay? But what I'm getting at is that if we can come up with the vector equation of that line segment, we can convert the vector equation to the parametric, which is just each of the components, right? This component is our x. This is our y, and that's all we need because we're in 2D space, and we're done. It's more efficient to do it this way than it is to do it by trying to find the equation of the line, et cetera, et cetera. So let's try and make this thing happen. I know this point was negative 2, 3. I know this point was negative 1, 0, right? What is the direction vector of this thing? From the bottom corner of the circle up to that one, what's my direction vector? It's 3. Hold on. You're subtracting it, right? So it's negative 2, take away negative 1, so you get negative 1, and then 3 take away 0 is 3. Right, that's my direction vector. What's my R naught? I know my V kind of looks like an R there. My R naught is negative 1, 0, right? I want to start here and go to here. So what is the vector equation of that line segment? It's going to be R naught plus TV. Isn't that convenient? I mean, we're already using t, right? T is the variable. I mean, that was our parameter. It's going to work. That t is going to work here too. So this is going to be negative 1 minus t, then 3t. Now, these right here, individually, these components are x and y. Those are our parametric equations. X is negative 1 minus t. Y is 3t. What's the restriction on t, though? What did I say? Anytime you want to draw a line segment, if you follow the pattern that I showed you, where you 0 to 1 always, right? 0 to 1 will draw that line segment. Starting out at negative 1, 0, it should start here at t0, and at t is 1, and we should be up there. So make sure we put our restrictions here. T is between 0 and 1. Can we check it real quick? If t is 0, where are we? Negative 1, 0. If t is 1, we are at negative 2, 3, up there. So I'm happy with that. So getting back to this, our parametrics were negative 1 minus t. Our y was 3t. And t, we said, was between 0 and 1. There. We have our parametric representations of both curves. Now, do we need ds? No, because the original problem asked for the line integral over c of sine x dx with respect to arc, not with respect to arc length, with respect to x, and then with respect to y. So we will need derivatives, but we will not need ds. We won't need square root of derivative squared. All right, here we go. I'm ready. I'm ready. Are y'all ready? Let's go. Call it a day. Let's get out of here before they shut the highways down, right? Okay, integral over c1 of sine x dx plus integral over c2 of sine x dx. So what I'm doing is I'm taking that first line integral, I'm breaking it up, it's supposed to be over c, I'm breaking it up over c1 and c2. Then I need the other line integral next to it, plus line integral over c1 of cosine y dy, and then plus line integral over c2 of cosine y dy. Any questions? Yes. That's a little more difficult to visualize. It's almost like, how can I explain it? Here's the best that I'll be able to do. Okay, if I show you this, right, it has an area to it. Yes, from your perspective, it has an area. If I tilt it and you don't know it's tilted, the area has now changed to you, hasn't it? So when we do, does everyone follow that? Like if I do it like this, it looks like a much thinner rectangle to you than it does if I do it like that. Yeah. So when we do it with respect to arc length, we're looking at this area across here. Here's the curtain, right? It's got a curve to it. And we're looking at it as a straight line across there. And we're looking at it from this perspective, saying, what's that area down there? Using the base, this width is here, right? With respect to x, we're looking at it from here. So we're not accounting for this. It's just the distance from here to here. So that area looks different from here than it does from this direction. Does that make sense? And then with respect to y, you're looking at it this way. Wait, hold on. With respect to x, you're holding dy 0. Yes, this way. With respect to y, you're holding dx 0, so you're looking at this. So you're only looking at the base being that instead of the hypotenuse. Does that kind of make sense? No? It's a perspective thing. It's a visual thing. Like, yeah. I mean, it's just the way it looks to you. That's all. That's the only way I can really explain it visually, I guess. Yeah. I don't want to get further into that, and we can get lost on that and never come back. Yeah. Let's do this first integral. This line integral over C1 means C1 went from 0 to pi, right? So this first one's going to go 0 to pi. All right. Sine x. What is x on C1? Cosine t. So this is going to be sine of, I better give myself some room. Okay, integral 0 to pi, sine of cosine t, all right, and then dx, which is the derivative of the x parameter with respect to t on C1, which was the derivative of cosine t, which is negative sine t. Yes? So times negative sine t. I'm going to pull the negative completely out and just put sine t right there. And then dt. That is integral 1 right there. Okay? If you like, that is that one. Then I have what? Plus now the same integral, it's the same line integral in terms of sine x dx, but it's over C2 this time instead of C1. So now what I need to do is figure out what the restrictions on C2 were. We said they were, what, 0 to 1 for our t? Sine of x, what's our x parameter on C2? Negative 1 minus t. And then I need dx, so what's the derivative of the x parameter on C2 with respect to t? Negative 1? I should just take that out, but I'll leave it. dt. That's our second integral that we'll have to do. There's 4, right? Plus C1 cosine y dy. So on C1 we were what? 0 to pi. Cosine of y. What was y? What was the y parameter? It was sine t. And then what's dy? What's the derivative of that? Cosine t dt. This is our third one here. One more. Plus, now we're on C2 again, 0 to 1. Cosine of y. What was y on C2? 3t. Then dy, which is derivative of y with respect to t, which is 3 dt. There we go. We're there. And then you go evaluate all of these. Basic substitution, u is cosine t. That would work here. That's, yeah. Basic substitution, right? So we could do all those, right? All right. Good. So maybe a question now would be the orientation of the path. What do you think happens if we change the orientation of the path? If we actually traverse the curve backwards? So normally, like what I'm doing is I'm starting out, I'm saying here's a curve C, right? We're choosing it in a way that we go from one point to the next, right? So in both of these, here I go from A to B here, but I could actually go backwards and go B to A, right? So if the curve in one direction we call C, traversing it the opposite direction, we say negative C. It means that path, opposite direction. Okay? What do you think happens? Do you think it changes the line integral? Don't think so? Why not? Okay, so you think that if we're doing a line integral over C with respect to arc length, ds, it shouldn't change. Do you all agree with that? because it doesn't matter, we're going to square the derivatives anyway. It's a square root of something squared, you know, added. It shouldn't change it. What if it's with respect to x or with respect to y, though? Well, that matters. So look, here it is. If you go and you want to do a line integral over c with respect to x, then if you traverse the path backwards, meaning that's the way we say backwards, negative c, then the line integral changes to a negative. All right? If you traverse the path c backwards and you're doing it with respect to y, it also changes the sign. But if it's with respect to arc length, it doesn't matter which direction you go, you're still going to get the same value. It has to do with, in the formula, it doesn't have anything to do with the dx, dt, the dx and dy necessarily, as it has to do with the time. The change in time is backwards, which gives you the negative on these two. And now that brings us to an even larger point, which is the idea of path independence. So given two points, A and B, what happens if we choose two different paths connecting the two? So if I go A to B, I want to get there. There's infinitely many paths, right? Do you think if I go along C and do a line integral along C with respect to arc length or with respect to x or with respect to y, one of those three, it doesn't matter, do you think that's going to give me a different value than if I go along C with the little squiggly as C tilde? So do you think that the line integrals along C and C tilde are the same? What do you think? What's your gut tell you? No. I mean, just think about the area underneath these curtains, right? I mean, these curtains hanging, those curtains are going to look completely different, aren't they? They're going to have different areas. So in general, these are not the same, in general. But it turns out that sometimes they are the same regardless of path. And that's the interesting stuff in math, is when we can come up with this idea of a line integral being path independent. So that if we want to try and do a line integral from connecting 2 points, if the function behaves a certain way, we can call it, you know, path independent. But we'll get to that. This just verifies what I just said. So let's try this. All right, so what we want to do is the line integral over C of y squared dx plus x dy, which is the same as the line integral over C of y squared dx plus the line integral over C of x dy. That's just changing the notation. This means this. Now, we're looking at the arc of the parabola x equals 4 minus y squared from negative 5, 3 to 0, 2. I want to look at that path versus the path that's just a line segment connecting those two endpoints, and compare the two results to see what we get. So what I think I'll do is I'll set up the line integrals, we'll plug it into Mathematica, and we'll compare the answers, all right? Just to prove to ourselves it's not the same. But I think there's some value in doing the parametrics. Would you like to try to do these? To set them up for quiz grade? You can work together? Okay, see what you can do. Do it on a separate piece of paper with your name on it. Sign-in sheet gets around to me, please, when it's time. So for the two separate problems you had, you should have had x was equal to 4 minus t squared, y was equal to t was between -3 and 2, right? The line integral should have turned out to be integral from -3 to 2 of y squared, so t squared times dx, which was -2t dt, plus you could do line integral from -3 to 2 of x, which was 4 minus t squared, dy was 1, so dt. Did y'all get that for the parabola one? I went kind of quick. That went very quick. Did y'all get that? That's where you're headed. Okay, but did you get this at least? Okay, right. That's what we talked through. And then now it's just replacing y with t, replacing dx with the derivative of this with respect to t, which is -2t dt. Then this one right here, since c is the same curve, it has the same limits of integration. We could put this all together in one integral. I'm just keeping it separate. And then x here is this. dy is derivative of t, which is 1. So that would give you this. All right? Y is t. Yeah? Okay, that's along the parabola. What about along the line segment? So along the line segment, the parametric equations, what did y'all get? I haven't even looked at this yet. 5t minus 5. 5t minus 3. Anybody agree? Yes? Agree? Yes? OT is 0 to 1? Okay. Sounds good to me. So your line integrals would be integral 0 to 1 y squared, which would be 5t minus 3 squared, dx, which would be 5, then dt, then plus the integral, same thing, 0 to 1, or we could put it all together, then x, which is 5t minus 5, dy, which is 5 dt. So that would have been along the other one. And if we evaluate, I'm not going to evaluate it, just trust it. Go Mathematica, Wolfram Alpha it, figure out. You'll see there are two different results. So even though we're connecting the same 2 points, they're different curves, we get different line integral results. And we move along. So the answer, in general, line integral depends on path. If we change the path, it's likely to change the path integral will change. Most likely the path integral will change. There are some conditions which make the value of the line integral independent of the path chosen. We'll address that later. All right. Now we move on to line integrals in space. So now instead of having a function of x and y and a curve down on the ground in the domain, now let's have a function of x, y, and z, and let's have our curve in three-dimensional space. Now we can't do a curtain anymore because we can't visualize it that way. We can't see the function and the domain in the same picture. So we can't drop a curtain and get an idea. But we can still define it, and it's still just an extension of what we just did. We have a curve in three-dimensional space. We have to find a parametric representation of that curve. This time it'll have x, y, and z. We'll still have a restriction on t. Or remember that if the parametric equations, they could come from a vector equation. And it doesn't have to be a line, okay? A vector equation where we have a vector function that draws curves. Isn't this the way we drew curves? We call these space curves. R of t, vector function. We drew like spirals and different things with this. So now what we can do is we can use those in the idea of this line integral of the scalar function f of x, y, z with respect to arc length. What changes here? Not a whole lot. You change your x, y, and z out for your parametric equations. Your arc length is different though, because now it's a three-dimensional Pythagorean identity. A squared plus b squared plus c squared equals d squared. And so you do square root, and so, But it's almost the same, isn't it? Yay or nay? Okay, but this is where things change. And this is vitally important because it's notation and it's critical that you see it. When we say this step right here, I want to highlight it. When we say f of x of t, y of t, z of t, when I say that, what we did is we took the scalar function, right? Everywhere we saw x, we replaced it with the t thing, right? The t was in terms of x, right? So we replaced that x with whatever our new definition of x was in terms of t. Then we replaced our y with whatever we had in terms of t, and then our z, right? We haven't done a z, but that's what we did in the previous two problems. Okay. This new notation, okay, this is this right here. Look at the new notation we're going to use. F of r of t. And it's a notation. It doesn't make a whole lot of sense if you try and think about what's happening, because you're trying to plug a vector, right? This is a vector into a function. That's not what we mean, though. When we actually write f, I don't know if, there we go. When we write f evaluated at r of t, at the vector function r of t, we're saying this. That's what we mean. We mean take the components of the vector function and plug the components into the scalar function. Does that make sense what I'm telling you? Look, I'll give you a quick example of what I'm trying to get at here, because it gets lost a lot. If I tell you right now f of x, y, z, I give you a scalar function, is the function x plus yz. All right? If I tell you plug in 1, 2, 3, you would say this is 1 plus 2 times 3, and that would be 7, right? Now, what if I tell you to do f of the vector 1, 2, 3? That doesn't make sense, because the function f is supposed to take numbers in, right? An x, a y, and a z in, and spit out an answer. It's not supposed to take a vector in. So when I write this, I understand it doesn't make sense. What I mean, though, is this. Okay? What I mean is you take the x component of the vector and plug it in for x, the y component of the vector and plug it in for y, and the z component of the vector and plug it in there. Okay? And if we agree that that's what we'll mean by that notation, then this notation makes sense. We're going to take the function f, we're going to plug in the vector function r of t. What was r of t? It was an x, a y, and a z, wasn't it? So that's the same as doing this. Follow? And then this right here is the big kicker. We replace all of this with this. What is the derivative of r of t? So go to your vector function. What is the derivative of this? Remember how to take the derivative of a vector function? Take the derivative of each component, right? So isn't the derivative of this, r prime of t, is x prime t? If r of t is xt, yt, zt, then r prime of t is a vector. It's x prime t, y prime t. We love taking derivatives of vector functions because they're super easy. You just do the derivative of each component, right? But then what's the magnitude? Because look at the formula. It's the magnitude of the derivative. What's the magnitude of this thing? Well, the magnitude of any vector is the square root of the sum of the components squared. So I would take x prime t and what? Square it plus y prime t square, blah, 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 blah. And isn't that exactly what this is? This is the derivative of x with respect to t squared plus derivative of y with respect to t squared, derivative of z with respect to t squared, square root. So that whole thing right there is just r prime of t, magnitude. So this is a really, really cool notation for a line integral in space, and now it has to deal with vector functions instead of, well, it has a scalar function, f, in here, but it's your parametric curve now is now a vector function instead of the parametric idea. And then dt, don't forget the dt at the end. Okay, as before, we can define three other line integrals. So if we have the line integral with respect to arc length, then it would make sense to do it with respect to x. So it would be the same thing, except you throw an x prime at the end. With respect to y, everything's the same except get the ds out of there and just do that. With respect to z, same thing. Don't ask me what this looks like. I'm not going to be able to explain it. I can't even explain what the original one looks like because it's so hard to visualize. Okay, and again, the three previous line integrals often appear together. So if you have this notation where it's just the this notation where it's a line integral only written one time, it's with respect to x, then y, then z, then what we mean is you do three separate line integrals. Find the line integral x squared dx plus y squared dy plus z squared dz, where c consists of the line segments, plural, 0, 0, 0 to 1, 2, negative 1, and then from 1, 2, negative 1 to 3, 2, 0. Did I tell y'all about this thing? How the OneNote like tries to name the pages? Have I told you all about that? How like when I write things in OneNote here, it tries to automatically name this page, like tries to read my handwriting and come up with a name for the page. Y'all see that there? That's what it's trying to name this. Okay, I'll open it up. This right here. This page is trying to call it sexy, 2. So I don't know where it's picking that up from. But it's funny, I've had this in the past where I've been writing, and I used to keep this open over here, and there would be like vulgar words in the, like it would come up with some stuff over there. It'd be like vulgarity and like really bad stuff. And then finally some student was like, you know, hey, why do you have like shit written over there? I'm like, it's not me, it's the program. Watch if I don't know what'll happen if I change it. I think once it chooses, here, I'll prove to you with this. See, I start with an untitled page, then as I start writing, see, it named the page for me, the. But sometimes it can't tell what I'm writing, so it starts trying things so sexy. It's funny. I saw that and I was like, okay, wonder if anyone out there sees that. All right. So if we want to do this line integral along C, do we all realize here C is two different line segments? So C is actually C1 union C2. It's two paths. So let's talk about C1 first. C1 is a line segment. It goes from 0, 0, 0 to 1, 2, negative 1. Now, because it's a line segment, and because I just reminded you how you do line segments, I can come up with a vector function that will start off at 0, 0, 0. It will move towards that other point. So the direction vector here is what? This is an easy one, right? 1, 2, negative 1, right? So I'm going from here to here. So my direction is just this minus this, so that's there, and then the original point. And restriction on t, 0 to 1. So r of t is really just, what, t, 2t, negative t, t 0 to 1. That's what's happening on curve 1. See, I'm no longer going to write down the parametrics because in the formula, I just need the derivative of this magnitude, don't I? In that new formula? Derivative of that, then the magnitude of that. Or magnitude of the derivative. Okay, tell me about C2. C2 is a little different. C2 goes from the point 1 to -1 to the point 320. So what's the R of t here? Starting out at 1, 2, -1, right, as a vector, plus t times my direction vector, which is 2, 0, 1. Putting everything together, we should get 1 plus 2t, 2, -1 plus t. Again, t is between 0 and 1. Everyone good with that? Any issues? All right, so let's try and do this whole thing. This line integral over c of x squared dx plus y squared dy plus z squared dz. That will be equal to the line integral on c1 of this plus the line integral over c2 of this. Oh, by the way, I just noticed right now, actually we're not going to do the derivative of r and take its magnitude. Why? Why am I not going to do derivative of r and magnitude? Because look at my line. My line integrals are with respect to x, y, and z. It's not ds. So yes, we will have to look at these as like the parametric equations are, this is our x, this is our y, this is our z. Okay, let's try and do this first one. Line integral over c1. Over c1, it's going to go from 0 to 1. I'm going to keep it all together. What is x squared on c1? So go up here. X is what? X is t, right? X is t. So x squared would be t squared. Times dx. Well, x was t, so 1. Dx would be 1. dt. Plus, how about y squared? So again, we're on c1, so go up here to y. Okay, y up here is 2t, right? So y squared would be 4t squared times what's dy? 2. So 2 dt. Now this is, I'm starting to get really bad notation because I can't have multiple dt's in here. What I need to do is just put another integral here if I'm going to do it this way, 0 to 1. And then I'll do another integral here, 0 to 1. Now I do z squared. What's z? Come back up here. It's negative t. Square it, t squared. What's dz? What's dz? Negative dt. So negative 1 dt. That is this. That's this. And then you go over here, but the difference is now you're looking at C2 and you plug in and you're done. Would dy be 0? What was where? On the next one? Oh, okay, yeah. Okay, yes, I'll write it out. We still have 2 minutes. This will be 0 to 1. It'll be 1 plus 2t squared times 2 dt plus integral 0 to 1. Y squared would be 4 times dy dt, which is 0 dt. And then you would have plus integral 0 to 1 of z squared, which is negative 1 plus t squared times d z, which is 1, so dt. That's what you would have there. So yes, it would zero out. The dy here would zero out this integral and it would be gone. So you wouldn't have to evaluate it. And then you have to compute all those integrals, and you could actually just take all the integral signs out and just make it one integral because they're all with respect to t. And they all go from 0 to 1. So you could even like combine like terms together. Use your properties of integrals. All right, everyone signed in the sign-in sheet here for the quiz grade? All right. I started to look at the next mini exam, and the first problem on that next mini exam, there's like one or two problems from like cylindrical and spherical integrals, and then everything else is like line integrals and some of the stuff we're doing later. So I'll probably send it out to you by Monday or Tuesday because you need a little more stuff before you can really get going on it. And I'd rather you focus some attention on doing problems in the book. So let's see if there's an assignment at the end of this. See if that's the right page. No way that's the right page. You can do 1 through 13. Odd. That's page 771. You could, whoa. You could do 1 through 13 odd. We have not really done the rest of those problems, 17 through 21. We haven't really done those yet, so you'd probably be hung up on that. Okay, I guess that's it, huh? Everybody have a good weekend. I'll see you back next week if we survive the cold.